Sally Cooper, a big Jodrell Bank welcome.
Hey everyone. Hi. So, in the modern world of dating, many of us turn to apps to find our perfect partner. But have you ever wondered what it was like to be an aging, dying star all alone? Well, I have thought about this, and so I created Spinder, a dating app for pulsars. And you'll hopefully have all read my disclaimer notice that none of these stories are related in any way to my personal life. So to start, I need to explain what is a pulsar. So, our Spinder profile, we have pulsar B1919 plus 21, which was the first ever pulsar discovered. And a pulsar is essentially a dead spinning star. So as a star evolves, it will do different things depending on its original mass. And something like the sun will evolve and eventually become a white dwarf, but those that are a bit more massive will expand into something called a red giant and then explode in a big supernova, and what's left is a neutron star, which is the core of that dead star. A neutron star is about 10 to 15 kilometers across, so they're really, really small objects. They're only about the size of Manchester, but they have the mass of about 1.5 times the mass of the sun. So they're incredibly dense objects. In fact, the only other objects in the universe that are more dense are black holes. So when I was doing research for this talk, I decided to set myself up as a pulsar on a well-known dating app. And throughout my talk, you will see various conversations that I might have had. So yes, pulsars are very, very dense, and I have no idea how that was meant in different ways. So the profile that I showed you at the beginning for pulsar B1919 plus 21 is the first pulsar that was ever discovered, and it was discovered by Jodrell Bell, as she was known then. And she was just a PhD student at Cambridge University, and she wasn't actually looking for pulsars. Nobody knew they existed. She was looking, in fact, for something called quasars using a method called scintillation. This is the telescope standing behind her. It's quite different to the telescope that you'll see, the beautiful Lovell Telescope outside. And this was back in the 60s, and the data, as it came off the telescope, looked a bit like this. It's like a pen chart recorder, so a bit the way you measure earthquakes, the way it's written out. And you can notice at the top where it says CP1919 is the signal that Jodrell Bell noticed, and it's now known as the scruff. And she saw it and noticed it was different to all the other data that she was looking through. And she wanted to know what it was. She was intrigued, and what they did was they worked out that it was definitely a non-terrestrial signal because it was appearing on the celestial time clock, essentially, so that we could say it was definitely from space. This is a recording slightly later on, and you can see just about this repeating pattern, these pulses, and that's where pulsars get their name, from pulsating star. Jodrell Bell as well. Well, the discovery of the first pulsar was awarded a Nobel Prize, to which Jodrell Bell did not receive. Her supervisor, Anthony Hewish, and another astronomer called Martin Ryle, both excellent astronomers, definitely deserved Nobel Prizes, but Jodrell Bell was missed out of that award. She has since been nominated for many prizes and always says that actually not winning was one of the best things that happened to her, because she's won every prize ever since. She recently won the breakthrough prize of about $3 million, which she's completely donated to the IOP, the Institute of Physics, for encouraging women and diverse background audiences into physics and astronomy. Woo! So I'm going to play you a little animation of a pulsar. So that signal that Jocelyn Bell received is actually, as the pulsar spins, it has a north and south magnetic pole, a bit like the Earth does. And out of those two poles, you have beams of radiation. And as the pulsar spins, that beam crosses our line of sight, our telescope, and we receive this signal. And this is its pulse as it crosses our line of sight. So you might recognize this image. It's the same as the artwork that was on the Unknown Pleasures Joy Division album cover. And what you're actually seeing in this is those pulses, as we saw from the animation, but stacked on top of each other. So as time happens, time is in this direction, and you start to see the build-up of those pulses. And they might look a bit different here, but actually over time, that is a very stable profile. And we can use pulsars as these really stable clocks. So in fact, the prediction of time using pulsars is much better than even atomic clocks. So to round up our first pulsar bio, they're located in the Milky Way. Nearly all the pulsars that we've discovered to date are found in the Milky Way. Obviously, they're likes, telescopes, my own space. They're fans of Joy Division and New Order. They like festivals. They don't like misogyny. So that's our first ever pulsar that was discovered. So I'm going to now take you through a few different types of pulsars through our dating app, Spinder. And this one is one of those really annoying ones, if you're familiar with dating apps, where you see a bunch of friends and you don't actually know who the profile is for. So this is Pulsar J1502, but we don't know which one that is. So this is actually a group of nulling pulsars, which means that that even though that pulse is really regular, for some pulsars they don't always behave the way we want them to, and they will occasionally turn off their emission, or we can't see it anymore. So they're literally going radio quiet on us. And some of you might be familiar with the term ghosting, or particularly this one, I like to call the ick, which is really, really super keen, really into them at the very beginning, and then turns off and you never speak to them again. And then we have different varieties, so actually this pulsar sort of turns hot and cold, on and off, and we see its emission intermittently. So I'm going to take this moment to introduce myself. I'm Dr. Sally Cooper, and I am a Pulsar Hunter. I work here at Jodrell Bank, part of the Jodrell Bank Centre for Astrophysics. And I have done research into searching for pulsars. And what I worked out when I did this is that my bio was actually exactly the same as a pulsar's. I enjoy the same things and dislike the same things. I even hula hoop, so I also spin a lot too. So a lot of the times while I was dating as a pulsar, I used the same line. As many people who are also familiar with dating know that you often get spammed with the same message, which is what I did to everybody else. So we're going to look now through a few more profiles of pulsars and their companions. And this system that I'm about to tell you about is the first binary system that we discovered, and it happened to be 2 neutron stars together. So that neutron star is that dead core of that star that's exploded in a supernova, and we call it a pulsar when we can see that beam of emission. So this system is a double neutron star system where one of those neutron stars is also a pulsar. I can play. So this is a nice video of this system, and what's really special about this case is that we can use it to test whether Einstein was right or wrong in his theories, especially of general relativity. So you can see that the 2 stars are in a very close orbit with each other, and what's predicted is that the orbit will actually shrink with time, and that's due to the release of something called gravitational waves. And to some extent, you don't really need to understand the axes of this graph, but what I want to show you is that shrinking of the orbit, as was predicted by Einstein, is the curve, and the observations of this system are the data points. And you can see how amazingly well that data fits to that curve. So I think that's one of the most beautiful things to look at. And this was, in fact, the first, was also awarded a Nobel Prize for the first indirect detection of gravitational waves. And this system, I sort of thought was a bit like that couple that talk for ages and ages. They're online, they've been speaking, and eventually that orbit is going to shrink, and 2 will become 1. So here we have another Spinder bio. This one is for the first MSP. MSP stands for millisecond pulsar, and that means, so pulsars have a range of spin periods, so how fast they're spinning. The first one was just over a second, relatively slow, but some of them can spin much, much faster. The first of these that was discovered actually spins 600 times a second. So one of the fastest things that we know on Earth that can spin that fast. So your kitchen blender, for example, spins only about a third of that speed. If you were to stand on the surface of the neutron star, you'd be traveling at about a quarter of the speed of light. Or to you and I, that's 100 million miles an hour. So this is something that has more mass than the sun, the size of Manchester, spinning 600 times in a second. The reason that some pulsars spin really fast is believed to be caused by their evolution. And I'm about to play you an animation of that evolution, and it involves another star. And so what you'll see here is a star that's about to go through its red giant phase and will become a pulsar. And then it also has another companion. So you can see it's growing in its red giant phase, big supernova, and you get a pulsar that spins relatively slowly, a normal pulsar. And that time later, the companion will also start to evolve. And during that time, the pulsar actually accretes matter. So it sucks in all that mass from its companion, and it will speed up the pulsar. And so that's how we get these really fast spinning pulsars. You need to have this companion with it. So this system, if you were dating pulsars, potentially you'd be worried about this other companion on the scene that's previously spun and wound this pulsar up. But what's interesting about the first MSP that was ever discovered is that we didn't find a companion with it. And that's because you can also find potentially when the second companion evolves too, in that supernova, you can disrupt the system. So it's a bit like maybe a divorce, and that's how you can end up with these isolated, fast-spinning pulsars. So one thing in particular for my next slide that you should know is the reason that the pulsar can attract the mass and matter from the star is because this companion, as it grows, overfills something called its Roche lobe, which means that its mass is no longer gravitationally bound to it, and that is called a Roche lobe. So another famous system is the double pulsar system. So in a similar way to we had the double neutron star system, there's another one that we found that actually has two pulsars. So they're a bit like that smug couple in their happy partnership. And so what I'm going to play you now is an animation about how this system evolved. So it starts out in exactly the same way as the other system that I showed. The first star will become a pulsar, a regular spinning pulsar, and then at some time later, the companion will also evolve. At that point, the pulsar starts to attract through its Roche lobe matter and spin up and become faster and faster. And now what's different here is that when the second star evolves, its original mass was also great enough that it would also become a pulsar. So this system is amazing. You essentially have these two clocks in space that are orbiting each other in an orbit of about 2.5 hours. So really, really close together. And so just in the same way the double neutron star system helped us test Einstein's theory of gravity, this system is essentially our laboratory in space where we can test this kind of physics that we can't do anywhere else on Earth. The thing with the double pulsar system is that one of the pulsars has recently gone out of view, and that's because of its spin. So you have these two axes, and what's happened is the pulsar does something called precession, which is a bit like a spinning top that starts to get a wobble. And that wobble means that the line of sight of the beam of the pulsar has now gone out of view. So even though this was our smug couple, it's a bit like when your friend is in this sort of happy relationship, they don't want to hang out with you anymore, and then occasionally they might come back when potentially the partner's gone on a stag or hen do. So we're hoping that this second pulsar will come back into view soon in the next few years. So we have another system, another profile on Spinder. This is for a system called a Black Widow pulsar. And so you might be familiar with the expression Black Widow in terms of spiders. And so Black Widow spiders, the females actually attack their partners once they've had all their baby spiders. Definitely not inferior. So this is our Black Widow spider, a highly destructive relationship. I'm going to show you an animation now of this system. So in the middle we have a pulsar. This is a top-down view, so like a bird's eye view of this system. And what you'll see is the pulsar spinning, but we also have another mass in the system, a companion. And that companion is tidally locked to the pulsar. And what's happening is the wind, this radiation from the pulsar, is actually destroying its companion, and it's just blasting off all of its mass. So you can see the pulsar spinning, and this companion, because one face is always towards the pulsar, a bit like the way the moon, you only see one face from Earth. That side is getting radiated and blasted away, and so you can see this hot spot on the companion. And what's interesting about this as well is that even though this is a really destructive relationship, one that I would advise you all to avoid if you ever date as a pulsar, is that actually the companion as well, even though maybe I made it out to be a bit of a victim, can block the signal of the pulsar. So in a way, it's not letting its emotions out to the world and to the universe. So this one, as my disclaimer, I'm just going to repeat the disclaimer again. Definitely, this one in particular has no relevance to my own life or to people in the crowd. So this system is a triple system, and these are really, really rare. So this is a pulsar in an orbit with a white dwarf star, and that is also then in orbit with another white dwarf. So there are three degenerate stars in this system. And triple body systems are actually inherently unstable, which is why they're quite rare. And actually, it's a mathematical problem to solve, and we're yet to have a solution to a three-body problem. And in these systems, it's actually highly likely that one of the stars will get disrupted and kicked out of the system. And potentially the pulsar will end up on its own. So beware of the triple system. So I've shown you quite a few different bios and profiles of pulsars. There are many types of pulsars. Three more, just really quickly, are planet pulsars, so essentially a single parent with kids. Ben Stappers, who's about to give a talk after this, can talk to you a bit more about how you detect other planets using pulsars. We also have the diamond planet, which is obviously the one that's looking for marriage, which is a system that we think is basically made of pure diamond. And also something called the cannonball, which I like to think of as the one, so some of the pulsars that we find, we also find associated, they're supernova remnants, so when they explode, they leave behind these beautiful remnants of all the mass that was ejected during that explosion. And you can see here in this image that the pulsar was actually ejected during that. And I sort of think of that as when you're leaving home. So I have to give a shout out to one particular pulsar that I was talking to. This is only a fraction of our conversation. And I just think it's brilliant. So hopefully you can all read that. And so a special thanks to my new pulsar friend. So I kind of want to wrap up a little bit in, I've kind of just bombarded you with loads of different types of pulsars, and the point wasn't really to get you to follow all of the physics with it, but to sort of understand that this has all happened in 50 years. And so this diagram is something called the period PP diagram, which is essentially the rate of the spin. So down here, we have the really fast spinning pulsars, and over here, we have the much slower pulsars. And on this axis is essentially the rate of change of that spin. So by how much are they slowing down? And this original plot is from the first 5 years after the discovery, and all those dots are the pulsars that we began to discover. And this image is building up every 5 years over those 50 years of all the pulsars that we've discovered to date. And you can see all of the slowish pulsars are over here grouped, All of the faster ones, they're labelled with blue if they have a companion. So all of those systems I talked about that have those companions are all grouped down here. And then further up here, we have all of the pulsars that are found in their supernova remnants. They're essentially the younger systems that have just been kicked out of home. And what I like about this is that this is in 50 years, and we've managed to learn about all these different types of physics and these groups, but actually there's still a lot of white space in this diagram. And so, what's next? What's the next system we're going to find? What is it going to be? Where's it going to fit in the PP dot diagram? Is it going to break our rules and theories that we have of pulsars so far? We've already had 2 Nobel Prizes awarded within those 50 years for pulsar discoveries. So I kind of want to dedicate this talk to all the single people because just like astronomers, there are plenty more pulsars in the galaxy and there are plenty of new bodies to be uncovered. But you could be just like Jocelyn Bell, and maybe one day you will also find your perfect discovery. So I'd like to say thank you.
Ladies and gentlemen, Dr. Sally Cooper, Pulsar Hunter extraordinaire. Now, we have time for a few questions. If you have one, please raise your hand and we'll bring you the microphone.
You said that pulsars are very dense, but you didn't. I don't think you said how dense. So, how dense is a pulsar?
Good question. So, the best way to describe it is by saying in comparison to other things. So, they are the second most dense objects in the universe. So, other than a black hole, they are the next most dense things that we know of.
Hi,
Hello.
thanks for the. Go on. Thanks for the talk. It was really interesting. I was interested in terms of the binary systems, how you actually detect them or find what they're there. Is it the interference of one body with another, or are there other ways of actually detecting them apart from interference?
Yeah, that's a really good question. So for the binary systems, we essentially found the pulsar first, but we noticed that the spacing between its pulses was changing and not as we expected it to. And it's similar to the Doppler effect, if you're familiar with that. So if you think of like when an ambulance drives past you and you get this change in frequency, what's happening with the pulsar and its binary is that because of its orbit, sometimes the pulsar is going to be moving towards you, in which case the pulses are more spaced more together, and then on the reverse, as it's moving away from you, again, it will cause a change in those pulses, and that timing is what's so important for pulsars astronomers, and they act as clocks, and it's that spacing that we can measure so accurately.
Hello there. I'm over here to your right. You mentioned the twin systems, the twin pulsar systems earlier, and they took 2.5 hours, did you say, to orbit each other? Okay,
Yeah.
How close are they to each other in order to be going around so fast? In miles and inches.
I don't know miles and inches. They are, I'm looking down at my front row of pulsar astronomers for a number. The radius. Okay, the diameter of the sun, thank you.
Hi, you mentioned a diamond system. How do you even know there is diamond inside that?
Sorry, which system?
A diamond system. It was like a star with diamond inside it.
Yeah, so I only really mentioned some of these other systems. So essentially you can get these really low mass companions with pulsars. And what we think has happened with the diamond one is that it's undergone, as a normal star, it's undergone some of its fusion, so hydrogen to helium, and then you get to carbon. But what's happened is for some reason that evolution has stopped, and so you essentially have this diamond star.
Oh, hey. I just wanted to know, if I was in a nightclub and wanted to dance like a pulsar, what would I do?
Thanks for that question. So pulsars have a rotational axis and also a magnetic axis. And they're misaligned. And so that's what causes the pulsing. So you have your north and south pole. And you're going to act as my telescope. So as I spin, I want you to beep every time my beam crosses your line of sight. Are you ready? Thank you.
Can you hear me? Yeah.
Yeah.
You got two binary pulsars, and they're going out together. They're swirling around one another, and they're getting closer and closer and closer. Do they actually form a black hole, or do they just form something, a bigger pulsar?
So in 2015, an experiment called LIGO actually detected it's essentially a double neutron star system that did. They collided and they formed one, and from that they emit this gravitational wave event, and that was detected in 2015 by LIGO, and so you can kind of see those ripples as the two stars were orbiting each other, and what you're left after a neutron star merger is maybe a bit unknown, but essentially you've got the mass of these two objects.
How old is the oldest pulsar, and what's the biggest age gap between the dating pulsars?
I love that question. So the ages, in the PP dot diagram as I showed with all the population of pulsars, it's actually really cool in that we can work out the age from just how fast they're spinning. So we do have a vague idea of how old these systems are. So the fastest spinning pulsars are often the fastest ones because they've had to undergo this extra sort of stage of evolution where they accrete matter from their companions. So they are normally the much older systems. And you get other systems which are much younger. They're the ones that we often associate with their supernova remnants, the ones that have only recently exploded, and we can find them still there. So that range of ages varies quite a lot by huge orders of magnitude. These are pulsars, not humans, so it's okay. And essentially, there are some pulsars that have their sort of mega years in lifetime. So we're talking zeros and zeros, sort of a billion, add some more zeros on, that kind of time scale.
Hi. You talked about when pulsars come into line of sight. So obviously, you can only detect the ones that do come into our line of sight. So do you actually have an estimate for the total population, maybe statistically, on how many pulsars there could be? But obviously, we can only see a percentage of them.
Yeah, so to date, we've discovered about 2,600 pulsars, of which I found 1%. In terms of total population, we estimate, so all of those 2,600 are in our galaxy, and we estimate that there might be a total population of, say, 100,000 neutron stars, but of which we might only be able to detect 10% of because of the alignment of these really narrow beams with Earth. So we think that there are probably at least 10,000 that we can discover because of the alignment, and what we need to do that is build bigger and more sensitive telescopes. And here at Jodrell Bank is actually home to the headquarters of a telescope called the SKA, the Square Kilometre Array, and this is going to be the world's biggest radio telescope built in South Africa and Australia. And with the SKA, we are hoping to be able to discover all of the pulsars in our galaxy that we think that will be aligned with us.
Oh yeah, really, really good examples there that you gave, really interesting examples. But to a layman like me, the names are quite inaccessible to remember the names of these pulsars. So are there any interesting examples out there with more accessible names, more publicly accessible names or anything like that?
So the names of the pulsars are actually their coordinates. So their right ascension and declination, so where they are in our celestial sphere. That's how they're named. It's quite boring. Some of them have nicknames, so like the double pulsar, and so we get familiar with certain ones. I have a particular favorite one, which I nicknamed, so all of mine just got boring coordinate names as well, but I have one called the Birthday Pulsar, which was a pulsar I discovered with a really similar spin period to another known pulsar. And to work out whether these two pulsars were different or if they were actually the same object we were looking at, we used something called Stirling's approximation, which is how you can, if you heard of that problem where you're in a room and it's like how many people does it take until two of you will share the same birthday? So it's the same problem basically, and you use something called Stirling's approximation to solve it. And we did that with these pulsars, and we found out, yep, statistically, these can be two different pulsars that are likely to share these spin periods. And when we discover a pulsar, we do confirmation observations. And the confirmation of that pulsar was made on my birthday, purely by coincidence.
Is there any reason that magma-towers rotate more slowly? At the front, sorry.
Right in front of me.
Yes, sorry. Is there any reason that magma-towers rotate more slowly upon average than the other pulsars?
Say that again.
Is there any reason why the magma-towers, so the high Tesla magnetic pulsars, rotate more slowly than the other type of pulsars?
So basically every question in science is we don't know. And to some extent that's true with magnetars, but essentially they're powered in slightly different ways, is what we think. So with an ordinary pulsar, the beams are powered by its spin. So with magnetars, there's something else, there's a different process that's happening. Not entirely sure what.
Hi, can you hear me?
Yeah.
Apologies, I missed the start of the lecture, but what actually happens during a supernova?
In a supernova?
Yeah.
In terms of just star evolution, there are sort of three classes of mass. So something like our sun is not massive enough to undergo this, and so when the star is undergoing fusion, hydrogen to helium, eventually, when it's in that stage, it's stable in the terms of its radiation pressure of all this fusion taking place is pushing outwards, but the gravitational attraction of all that mass is actually what keeps the star stable. However, when it gets towards the end of its life, that equilibrium is thrown off, and you get something called the red giant, and that's when it begins to expand. And for stars that have a mass originally big enough, they will undergo this supernova, and essentially it blasts off all of the outer layers from the star, so that's why you're left with this really, really dense neutron star at the end. And it's an instantaneous explosion, absolute cataclysmic. When supernovas take place, they're the brightest things that you'll see in the sky.
It all happens in seconds.
Yeah.
Thank you.
Thank you. Over here. Sorry. Hello. Really good talk. Thank you very much. Now, I'm hoping I haven't misread the chart you showed, but you showed a chart that showed clusters based on speed of the spin, and you showed that the fastest ones tended to have companion stars. Yeah?
Yeah.
And then you said that as the pulsar gets older, it gets faster. So is there a connection between the age of the pulsar and the likelihood of there being a companion star? And is there a causal effect there at all?
Yeah, exactly that. So you can basically throughout this diagram, you can see the lines going in this direction, and that essentially denotes age. So you have the much younger pulsars in the top, and the older ones as you come down this way. So, like we said, with the fastest spinning pulsars, they have to undergo this extra stage of evolution where they have this companion and accrete mass, and that takes time. And they've already undergone their own evolution to become a pulsar in the first place. So they're the ones that are the much older stars. And all of these down here are the fastest spinning stars, and all of the blue ones are the ones that have been found with companions. So that kind of backs up the idea, that theory of evolution of these systems is also the oldest pulsars as well.
Hi, you all right there?
Hello.
I enjoyed that talk, thanks very much. Just asking about the secondary companion pulsar, when it's formed, will its clock speed increase at all, or will it stay the same because there's two pulsars in the system now? Will its speed ever increase, or will it be fixed at that rate because they're both pulsars? Does one pull material from the other to increase their speeds, or will they stay at then the same rotation speed?
Periods of both pulsars with time will it will slow down. So that's what happens with all of the pulsars. They eventually are slowly spinning down. And that's the same for the double pulsar system too.
All right, everyone, thanks very much. That's all we have time for. Give her another round of applause.